Hello, Evan. How art thou doing on this fine dandy day?
I'm doing absolutely fantastic. And it looks
That
like we
is,
have quite a few other people as well with us who are doing fantastic, hopefully.
it better be. Otherwise, I might have to have some words with them.
Yeah.
Yes, hello.
Hello, everyone. What time is it where you guys live? I know we usually get people from all over.
I think I know what time it is where you live, Evan.
Yeah. I think you might. Would make sense.
Yeah, it would.
Orlando. Ooh.
Orlando. That's a fun spot. There's a lot of bugs there, but still pretty fun. Texas is nice.
7, yeah. Anyone who's in one of my live courses will know that I always ascertain that Pacific time is by far the best.
Yeah, who would disagree with that?
Yeah, I don't know. Maybe someone who doesn't live in Pacific time. Oh, and here's a riddle while we burn some time. The one who makes it has no need of it. The one who buys it rarely uses it. And the one who uses it never knows that they do. What is it?
Do you want to put that on the screen, or I can type it up real quick?
Sure.
Okay. The one who, could you read it again, Evan?
Sure. The one who makes it doesn't need it. The one who buys it almost never uses it. And the one who uses it, well, they should and almost never know. Actually, they never know. The times they know are statistically insignificant. Ooh, fate, that's a good idea. But it actually is something different. Oh, oxygen. I mean, who? Oh, Enoch. Yes, it's a coffin.
Woo, coffin.
Although
dealing with our own mortality. Woo.
Yeah. But hopefully none of you need coffins anytime soon. Oh. Fortnite Battle Pass.
I think people know if they're using a Fortnite Battle Pass.
Unless you like snuck it into their computer or something.
Maybe.
Oh, our videos are on screen now. Hello.
We have reached the final frontier of Riddle. Now Riddle is also on the screen. You know what else is on the screen? The chat. And do you want to know how your chat message can appear on screen? Well, it's pretty simple, actually. You just send it as a direct message to Chat Relay. And then you might even get some stars showing up next to your name. For example, I see Mike, I think that's pronounced. Mike will now have a star. See, look, Mike has a star. Good job, Mike. Everyone is getting stars now.
Yeah.
I don't know who our moderator is today, but they are smiling on you right now. You should thank them.
Yes. And actually, stars reset after 10 minutes. So you're motivated to always send good messages to keep your star count up. Star, 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 star. Oh, and it's right around time. So I'm actually going to introduce this person who you may not see at the moment, but you certainly will later. Megan.
Hello.
Now you see her. And now it's me again. I'm so sorry. But while we're here, Megan's actually qualified for national math counts, has made Amy countless times, and is the president of our school's math club. Some would say dictator, but she's here, so let's not discuss that. She's actually played violin since she was 5 years old, which is a really long time. Because when you're 5, you're like 3 feet tall or something. I don't know. Oh, and she also confuses the EU, how to pronounce it in Euclid and Euler. Or is it Euler?
It's Euclid and
Euclid?
Euler.
Yeah, well, we all do that, I suppose.
Yes. And the lovely human who was just now speaking is Evan. Evan believes I am the dictator of our math club because he is, in fact, the vice president of our math club, not the president. And so he has small amounts of resentment. He has qualified for USAJMO, as he prefers to pronounce it. And he's also gone, that isn't correct. He has qualified for math counts twice and attended 0 times because of the pandemic. So welcome our most lucky of co-hosts, Evan Lim.
That's a good introduction. Thank you. Thank you. I'll send that money to your Venmo in just a bit.
Yes, thank you very much. Okay. So I think then, without further ado, it's probably about time to get started with what you all are here for, which is unfortunately not our amazing personalities, but instead these amazing questions. So, what is our first question? A fair coin is flipped at the start of each of 2 water polo games. For each game, Lily's team gets the ball first if the coin lands on heads, and Natalie's team gets the ball first otherwise. What is the probability that Natalie's team gets the ball first for both games? And we're just going to express our answer as a common fraction. So, what do we do first? So we're trying to find the probability that Natalie's team is getting the ball first for both games. And the thing that I first notice is that, there is a solution for that, and
it's on its way.
It is on its way, yes.
Yeah. Oh, that's okay. Well, actually, while you're doing that, we can draw your attention to the wonderful reds, blues, purples, reds, and grays. They're very mathematic colors.
They are the most mathematical of colors.
Yeah, I agree.
See, they're the most mathematical of colors because those are actually Evan's colors when we get to see Evan's screen again, and Evan is the most mathematical of all humans.
Of course. There's no one who math more me. Mm-hmm.
Yeah. Except for maybe your sister. Your sister might math more than you.
Oh, yes.
I say this without any bias whatsoever.
I like what you say, Ethan Johnson. I actually am the creator of all math.
Well, thank you very much for sharing the mathematics with us, free of patent fees, Evan.
Oh, cool. And as you can see, the colors. Wow.
Woo! Okay, so what we should be able to do then is you guys should be able to see the problem that I have read, and we will talk about how we are going to solve it. And so that's actually going to be pretty simple, because the first thing we're going to see is that coins, they have a very bad memory. When they think of absolutely nothing. So our first coin flip is not going to affect our second coin flip. So what's the probability that Natalie's team is going to get the ball for the first game? Well, that's going to be the probability that we don't get a heads. The probability that we do get a heads is 1/2. So the probability that Natalie's team is going first is 1 minus 1/2. Or 1/2. And this is the same for the second one. And since our coin has no memory, we are just going to multiply these two and get 1/4. So yeah, like people are saying in chat, just 1/2 times 1/2. And yeah, we have to remember that it says that we are going to need to express it as a fraction. I think it says that right there.
Good point. A lot of these competitions, they try to trick you. And sometimes they'll even say express as a common, express as a decimal rounded to so many digits. And you have to be really careful that you give them a fraction if they want a fraction and a decimal if they want a decimal. Yeah. Or if it's math counts, you don't give them any units, which is just a small thing.
Yes.
Cool. Yeah, that was a good solve. And the answer is 1/4. Okay.
Woo.
Yay. Sprint number 9. How many arrangements of A, B, C, D, E are there such that the A is not to the left of B and the B is not to the left of C? Okay, so the A, we cannot have something where A and then some other letters and B. And we can't have something where B is to the left of C. We can't have B, C. And since we can't put them in the same spot, that means we have to have B something something then A, or just BA. It just A needs to be to the right of B. And then here, B needs to be to the right of C, because we cannot have B to the left of C, and they can't be in the same spot. So basically, we want to find the number of ways to fill in 5 spots with some order of C, actually with CBA in this order, and then a D and an E somewhere. Well, there's probably a faster way, but for this one, I actually just want to do it counting if we have C, B, A, then we will have 2 other spots. Oh, I wrote over the problem. Sorry. C, B, A. And there are 2 other spots somewhere. And now the C, B, and the A, they can be on the left, in the middle, or on the right. So there are 3 ways to place it. And then we'll have 2 spots, 2 for the D, 1 for the E. That's 2 times 1. And there's 6 if they're all together. We could keep going like this, but that's kind of slow, right? And actually what Gareth is saying in the chat is a lot better. We don't want to count every single individual one, because that's going to take us probably not all day, but most of today. Instead, we can say that A to the left of B is exactly as likely as A to the right of B, and B to the left of C is exactly as likely to C of B to the right of C. So half the time we'll have A to the right of B like we want, and half the time we'll have B to the right of C as we want, which means that 1/2 times 1/2 equals 1/4 of the time we'll have an arrangement that satisfies the requirements. And then how many total ways are there? Because we want 1/4 of that. Well, that's just 5 factorial, or 120. So we can take these out. And our answer will be 5 factorial over 4, which is 120 over 4, or 30. And is that right? Let's see.
Or is it?
Oh no, it's 20. What did I do wrong? Let's see.
That is a very good question.
Oh, whoops. I just see. What did the problem say? So A must be to the right of B.
Oh,
And,
Evan,
oh,
you should
sorry about that.
pull your writing down. Just give it a little tug.
Yeah, I will do that right now. Okay, and I think the reason this is wrong is it's not perfectly 1/2 times 1/2. Yes, yes, like what William is saying in the chat, because when we have, let's see, A to the right of B, sorry, did that again. We want A to the right of B and B not to the left of C, so B to the right of C. Dun, dun. Okay, oh, the C went away. And this CBA isn't going to happen 1/2 of the time. No, that's wrong. It's going to happen 1/6 of the time because there's 6 possible ways to arrange A, B, and C. So that means that CBA, of all the ways we can arrange ABC, ABC, ACB, and so forth, this is going to happen 1/6 of the time. And then the answer is just 120 over 6 or 20. Haha. And yes, it hasn't changed. Great. Cool. And yeah, that was I'd say an easy mistake to make.
Yeah, definitely. It made a lot of sense until it just didn't.
Yeah.
Isn't that fun?
Yeah.
Yes.
Another thing, oh
yeah.
Never mind. Another thing that made a lot of sense until it didn't was a few days ago in physics class. We thought we had invented a perpetual motion machine, but we had just done the right-hand rule wrong. So.
Oh my goodness, Evan. Only your physics class would think that they could just break the laws of physics and it be correct.
Well, we had a chance. Okay.
No,
What's the next one?
The next one is asking what the 10th smallest positive multiple of 10 that is not divisible by 2 cubed or 5 cubed.
Ooh.
So that is a very good question. And honestly, I think I could just bash this out, but I don't want to do that. So do I? No. Let's do a fancy bash where we'll basically, it's like bashing, but a little bit nicer. So, okay, we know it's a multiple of 10. So we already know that it has 2 to the power of x, where x is at least 1. And that's not a 5. That's a 5 to the power of y, where y is also at least 1. And we know that both of these have to be strictly less than 3. Cool. So we can either have the powers of 2 and 5 be 1 or 2. And that is about it. So what can, yeah? Oh, is there something, someone say something cool in the chat?
Yeah, I think we can just list, is it? Yeah, couldn't we just list out multiples of 10 and see which and cross them out?
Yeah, definitely. I'd guess that we would end up listing like at most 15 to 20. And yeah, it's probably more efficient.
I see what you mean though about a smart bash. Maybe we could list out like 1 through 20 or something.
Yeah. One thing I would say though is we can also, we know that suppose we said our last number is 100, right? Well, we know that this can't be true because we have to deal with the powers with 2 to the 3rd power. So that is going to be 40 and 80. So now we put our new guess at 120, but because there's 2 more to account for these 2.
Yeah.
These 2. But 120 is also divisible by 8. So that means that our final number is going to be 130, and that doesn't add any new numbers. So that's one way that we can definitely do this. I feel like there's a lot.
Yeah.
Yeah, we can definitely just go write them out, but that's kind of boring. Like, it's a good strategy, but I believe in all of your abilities to write 13 numbers. But yeah, like people were saying in the chat, it does turn out here that 5 cubed is going to be too large. So yeah, we're just skipping the multiples of 40.
Yeah.
And is that correct?
Let's see.
Yes.
Yay.
Woo.
I like how you, instead of just doing the first bash that came to mind, did a much more kind on the fingers bash. Yeah, that was nice. Okay, let's see, what's the next question? Oh wow, there's a lot of words, darn. The cross section of Sakura Mountain through a straight trail to the peak is in the shape of an isosceles right triangle, which means that these two bases, they're of equal length. With the slope upward being the hypotenuse of the triangle, okay, that's what they're climbing. At a certain point along the climb, the altitude is equal to the remaining distance along the slope to the peak. What is the ratio of the altitude at that point to the altitude of the peak, assuming the base is at sea level, which is just altitude 0? Okay, expressed to the nearest tenth. Okay, I'm actually gonna underline that quickly so I don't forget. Nearest tenth. Looks like I crossed it out. It doesn't matter. Okay. See next slide for just the diagram. Okay. Cool. So we want the altitude. I'll quickly write that out. Altitude equals the remaining distance along the slope to the peak. Remaining climb. Okay. Well, we could guess that if we estimate it, it'll be, oh, how convenient. They gave us it. It's right here. And then the altitude. Okay, we could just say A for altitude. Then because they're both isosceles right triangles, this here is A, and this is A root 2. I don't know. Do I want to do it this way? It's okay doing it this way. So this one's A, and this one's A root 2. And then so I don't really confuse things. Or actually, I just had an idea. I'll let the side length of this mountain be 1, just for fun. But since they didn't give us a specific side length and they want a ratio, it's okay to let it be whatever we want. So this is 1, this side here, and this is 1 minus A, 1 minus A. And because this is a right triangle with 1 and 1, this long hypotenuse, the whole one, is going to be root 2. So this little distance over here is root 2 minus A square root of 2. From here to here. Okay, and the altitude, this altitude equals the remaining climb distance, and that's our equation. A altitude equals the remaining climb distance, which is root 2 minus A root 2. Or moving the negative A root 2 to the other side, A by root 2 plus 1 equals root 2. They want this in the nearest tenth. Oh, yeah, good. Our denominator is actually going to eventually become 1. That's nice. And from here, A equals root 2 over root 2 plus 1. And I'm going to actually move this up a little so it's easier to do work. Okay. And then root 2 over root 2 plus 1, I don't want to divide that. It's going to be messy and hard. Instead, I can rationalize the denominator by multiplying by root 2 over root 2 plus 1 by root 2 minus 1 over root 2 minus 1. And this is just 1 because it's something divided by the same something, so it's 1. But the denominator is actually going to simplify to an integer by difference of squares because we have root 2 plus 1 times root 2 minus 1. that's going to be root 2 squared minus 1 squared, which is just 1, which is, oh, that's nice. 2 minus root 2. And what did they want? Ratio of the altitude to the altitude of the peak. Oh yeah, and that's also why I chose this side length to be 1, because then when we're dividing the altitude by the altitude of the peak, that just ends up being a over 1, or a, which is 2 minus root 2. That's nice. So our answer is going to be 2 minus root 2. And at this point, I'd probably just box it on my paper and move somewhere else to actually do it. And root 2 is 1.41, but let's see, nearest 10th. So 1.41 is effectively 1.4. 2 minus 1.4 is 0.6. And that will be to the nearest 10th, I hope. Let's see, is Chad agreeing? Oh, I see some.
I think Chad is agreeing for the most part. We have some different answers though, but those could just be rounding error.
Yeah, like it would be, if you rounded root 2 to 1.3, then you would get that equal to 0.7, which is not right. I imagine. I certainly hope it's 0.6. Oh, cool. Chat's agreeing. And yay, it is 0.6.
And
hooray.
Just for the rest of chat who's asking, while Professor Lowe would have loved to be here, he was actually off at MIT helping to grade the, how do you pronounce it, Evan? The USAW AMO or something like that?
USAW Ma'oa. I don't know. I can't
he was helping to grade that. So yes, unfortunately, you're stuck with just us. It's not actually that unfortunate. We're quite fun to be around.
Yeah. Oh, and Kamal, you lost all your stars because every 10 minutes the star system resets. So you can't, like, in the beginning send tons of really good messages and then just spam the rest of the time and use your stars as insurance. Yeah.
I like the math essays in the chat. Like, yes, math does become your second English class at some point. It's really unfortunate. Speaking of which, here is a math essay, except for this time, it's a problem. Okay, Miriam is putting together a jigsaw puzzle where all the jigsaw pieces are equilateral triangles with side length 1 centimeter. We have one like that, actually. The completed puzzle with all jigsaw pieces put in place is a regular hexagon with side lengths 10 centimeters. Her starting pile consists of all the edge pieces, which are jigsaw pieces not completely surrounded by other jigsaw pieces when in the completed puzzle, along with 35 other jigsaw pieces. What fraction of all the pieces in the puzzle are in Marian's starting pile? Okay, and we're expressing our answer as a common fraction. So we've been gifted a diagram. If we scroll the correct way, that is. We've been gifted a diagram. No, I didn't. No, I didn't. See, I didn't show you the answer. You said the answer, and that's the difference. No, see, I didn't show any answer. I don't know what on earth you're talking about. But what I did show you is the amazing diagram that we have gotten. And so what I'm going to start out with is I am going to look at the edge pieces of our diagram. You know what? This is a lovely diagram, but also it's a little bit small. So I think we might real quick whip up a small portion of our own diagram. Let's come over here and actually, we can just see the Megan diagram. Yes, Evan?
Yeah, what Megan's doing is a really good strategy on math competitions when the diagram is either tiny or just really unclear. You can use their diagram as a motivation to draw your own. And a lot of the times you can clip out the unnecessary stuff.
Yeah, I think we can probably get by just fine with a segment of a diagram that's going to look like this, basically. There we go. So we have our portion of a diagram, and now we want to see what our edge pieces are. Well, that's going to be this piece, this piece, this piece, here, here, basically all of the pieces along the edge. Well, and so what I notice here is that we can look at just one triangle like this, and you will get the same results just on a 1/6 of the scale. So what does a triangle look like? Well, that's a pretty simple question to answer. It looks like that. And just as a reminder, our edge pieces are still this one, and this one. Now, let me actually pull back up our problem because, well, it was an incredibly long problem, and I want to make sure that I answer the correct question, because otherwise I will do all this work for nothing. Okay, yes. Okay, but yes, we have this up here now. So we can see that, oh, interesting. For starting power of all the edge pieces, along with 53 other. Evan, am I reading this correctly? Because here's what stands out to me when I look at this. Mm-hmm. We've argued that each of our 6 equilateral triangles will make up our hexagon, and they'll fit together. So the number of edge pieces and the number of non-edge pieces would be a number of 6, right? Mm-hmm. Or multiple of 6. Yeah. 35 is not a multiple of 6, is it? I'm not going crazy here.
35. No, I don't think so.
Okay.
Actually, I think it's just that maybe she has where is it? Here. Maybe she just has like this piece and this piece. Yeah.
Oh.
But I think what you're doing will work. It's.
Yes. Okay. Yeah. So that makes this pretty nice. So as we can see here, in our larger diagram, we're going to have 10 of these 1-inch edge pieces per triangle. So that's going to be 10 and times 6, because remember there's 6 triangles, and then plus our 35 random is going to give us our total of 95 pieces in our starting pile.
Oh, do you know if we have to count both all of these as edge pieces? All of them along the edge?
I don't think so, because I think those inner ones just share a point, right?
Oh,
and
yeah, and the
our edge pieces, they're technically surrounded.
Yeah.
On all 3 sides. So I don't think so, but that is a good question. But yes. Okay, so we'll keep going off of that assumption. Yes, and we will say that we just have our 95 as our numerator. And then for our denominator, that's pretty simple as well. We are just going to use the number of triangles that appear in one of these equilateral triangles, and we could count them. But I don't want to do that. If we look at Evan's diagram,
it's big. Counting
it's
it will take
big.
a long time.
Yeah. So what I'm going to do instead is I'm going to remember that this is actually going to have n squared. Well, here n is 10. 10 squared smaller equilateral triangles within it. And then we multiply that by 6 for each of the 6 triangles. And that would be giving us our answer. So yeah, like you guys are saying in chat, and then we just simplify this to get 19 over 120. Yes, and if any of you guys have questions as to how we got the 10 squared, I can definitely go over that. There's a couple of cool ways actually where we can see that. But yes, in the meantime, let's double check if I got this correct.
Looks right. Yay.
Looks right, yeah.
Okay. I will take off this diagram.
Okay, yeah. Real quick while you do that, I'll just go look real quick at why we have the 10 squared. And so there's actually 2 different ways that we can do this. And way 1 is pretty simple. And that is just going to be each of the smaller triangles has 1/10 of the side length of the larger one. And thus by, do you know the name of the law I'm talking of, Evan? Is it like the law of proportions or something?
Sure what
it's going to be the law that means that if this is the side length, then the area is going to be that square. It's going to be 1/100th of the area.
Yeah, I don't know exactly what law it is, but you could also think of it as if you had a square and then you scaled it down to half of its dimensions, then each side length is half. So then the overall area is 4. And for 2D figures, that will always be the same.
Yeah. So yeah, and then there's actually one other cool way that we can look at it. And that's just going to be that when we have our triangle with its little triangles in it, that's a diagram. If we look at just the new row that we've added, we'll notice that, so we started with something wrong. We don't need a highlighter for that. We need a pen. We started with something of length n, and then we add n more triangles. Those are the ones with the pointy bit down, and then n plus 1 with the pointy bit up. And that actually is how we find the difference between consecutive squares.
Yeah, I actually haven't seen that way before, but it's really cool.
Yes. Yeah. So yeah, there's a couple of cool ways we can get that because math is pretty cool, isn't it, Evan?
Yeah, it is. And yeah, Sean, that's right, what you're saying here. And actually, if it was a 3D figure and you scaled it down by 1/10, the volume would be 1/10 times 1/10 times 1/10, which is 1/1000. Yeah.
The surface area would actually still be 1/100 though.
Yeah, because it would be 2D.
Yeah.
That would be more of an understatement. Math is really, really cool. Okay. Next question. Aha! Right away, without even just reading the question. All these are powers of 2. 2 to the something, 2 to the something. 4 is 2 squared, and root 2 is 2 to the 1/2. That's going to be helpful. Okay, so let these be 3 consecutive terms of a geometric sequence where B, C, and A. Wait, where is C? Oh, there's 3 consecutive terms of an arithmetic sequence. And then what is the value of C? Okay, they want C. I see. I see. Haha. Okay, express your answer as a common fraction. Well, we can start by doing what I alluded to earlier. 2 to the b. That's 2 to the b, of course. 4 root 2. That 4 root 2 equals 4 times the square root of 2. 4 is 2 squared. Root 2 is 2 to the 1/2. 2 squared times 2 to the 1/2 is 2 to the 2 plus 1/2, which is 2 to the 5/2. And then 2 to the a. Okay, that's nice. Right here, I see a way to finish the problem. Yeah, like what William said, you can finish the problem because by the nature of a geometric sequence, we're multiplying something, let's call it r. We're multiplying by r to get here, to 2, from 2 to the b to 2 to the 5/2. We're multiplying by r again to get to 2 to the a. So we'll have that the product of 2 to the b and 2 to the a is the same as 2 to the 5/2 squared. And so 2 to the a times 2 to the b equals 2 to the 5/2 squared, and 2 to the 5/2 squared is 2 to the 5/2 times 2, which is 2 to the 5. And then because of how exponents work, this becomes 2 to the a plus b equals 2 to the 5. So a plus b equals 5. Good. And we actually did all this because they want c. And because c is the middle term in an arithmetic sequence with b, c, a, then c is the average of a and b, or half their sum. Okay, switching to the answer color of green. C equals a plus b over 2 from the arithmetic sequence. And from the geometric sequence, we found a plus b is 5. So c is 5/2. Let me see. Oh, good. Chat is agreeing. Oops. Yay. Okay.
Chat's pretty fun today, aren't they?
Yeah, yeah. They get the right answers.
I mean, to be fair, chat's fun, regardless of the correctness of their answers.
Oh,
Chat's fun.
definitely.
Chat's fun when chat is being nice and respectful. Which,
and when it's on screen, this is really nice.
yes. Okay. Yes, we have a new question up here, and it's just asking how many 2-digit prime numbers do not divide any perfect cube under 2022. And we are given that there are 25 prime numbers less than 100. And so I think that is I think if they're telling us that, then it's pretty useful. So I want to make sure to remember this. We have 25 primes less than 100. Do not divide any perfect cube. Okay, interesting. So if a perfect cube, because I know that if we have a prime that divides a perfect cube, then this means that our prime divides x, right? And so we want to figure out basically now how many 2-digit primes divide an x such that x cubed is less than 2022. So we get a calculator for this, right, Evan?
I don't know. Actually, you may not need one. Wait, let me think for a second.
Okay,
Wait,
well,
no.
even if we don't get one, we have someone in the chat with the very big brain letting us know that 13 cubed is 2197.
Mhm.
And you might notice that that is in fact bigger than 2022. And 11 cubed, I know that's 1331, which is less than 2022. So this means that the only two-digit cube that is that the only two-digit prime that divides a cube less than 2022 is, well, like Chatmod has said, 2, 3, 5, 7, and 11. And so now we have basically two choices here. We can look at the number of two-digit primes and subtract 11, or we can look at all of the primes less than 100 and subtract 5. The first option is a roundabout way of doing the second, so I'll just do that. 25 minus 5 equals 20.
Yay. I think that is the answer. Yeah.
I hope so. Nope.
It is.
Yes.
Cool. Yeah. That was good. I like how I probably might have gotten tricked into starting listing out all the primes under 100, but then they tell you, and we can just subtract the one-digit ones. Okay. Convenient. And the next question. Oh, probability. A jar contains, oh wait, counting, not probability. A jar contains 36 colored candies, each of which is either red, blue, yellow, or green, and otherwise identical. Okay. There is an equal number of candies of each color. Suppose 10 candies are selected from the jar. What is the number of possible combinations of candies? Well, I'm going to, yeah, the order is not going to matter. It's just going to matter like how many red, how many blue, how many yellow, or how many green we have. And we're actually going to have 9 of each because there is an equal number of candy of each color. 36 over 4 equals 9 of every color. So, you know what? It's actually really tempting to list out like how there's 9 of one color and 1 of another color and 0 of all the rest. Or maybe there's 8 of one, 2 of another, 8, 1, 1. But actually, we don't need to do that. And that's a pain as well, because they're 9, and 9 is really close to 10. So we can use sticks and stones, or stars and bars, or baskets and bagels, or I can't think of anything else. Any other
Baskets and bagels is only for you, who is obsessed with bagel pico fermi, Evan.
Well, more the bagel of the bagel pico fermi.
Are pico and fermi even like tangible objects? This is the true question of life.
Oh yeah, so we have our 10 candies, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And if we just put in 3 dividers somewhere, 3 dividers, we could just say that all of the ones over here are red. These ones are blue, these ones are yellow, and these ones are green. And the only time we'll have a problem is if it's like divider, 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 and then 10 candies, or 10 candies right between 2 dividers. But that's really easy to subtract at the end. The only time that would happen is if we had 4 of any candies, 4 of any colors, 10 of any of the 4 colors. And there are only 4 ways of that happening. But since we thought of it now, we'll just write something minus 4 and probably circle it. Or if this was paper, I'd probably poke a little hole next to it so I don't forget. And then this is normal stars and bars, sticks and stones, biscuits and bagels, or whatever I said the other one was. 10 candies, 3 bars. 10 plus 3, choose 3. 13 choose 3, which is 13 times 2 times 11, because 12 over 6, I just skipped a step in my head, that's 2. And that's 26 times 11, or 286 by the multiply by 11 trick. 2, 6, 2 plus 6 is 8. Oh, and then we mustn't forget the minus 4. So we had 286 minus 4, or 282 ways. Okay. Oh, I see Evan. Oh yeah, I like your name in chat. Also saying that the number of ways, if we don't account for subtracting 4, is 286. Oh, Sean, we subtract 4 because stars and bars, it might give us a situation where all of our bars are on the left side, say. So we have bar, bar, bar. And then all our 10 candies, which would mean we had chosen 10 green candies, but there are only 9 green candies. So that wouldn't work. And the only time that happens is if we have, or the only time we choose something that's not there is when there are 10 of a candy. And that can happen 4 times because of the 4 colors. So we subtract 4 and get 282. Whew. Let's see.
That was a
Yay.
tricky problem.
Yeah.
Good job, Evan.
Cool.
Okay, what is our next problem?
Unit squares. Oh, I'm glad you got this one.
Unit squares are not that bad.
A lot worse than
Okay.
squares of side length 2.
Oh my goodness. We're doing a probability. It could be a square of side length 2. I mean, we have to adjust the other things, but still, it could be, Evan. You don't know.
Okay. Okay.
Okay. So that's the diagram, but we should probably also look at the problem. The problem is asking if we have A, B, C, D, the unit square, point E is randomly chosen on CD, what's the probability that the smaller of the two distances, EA and EB, is no more than 1 plus 1 over 24? So here is our handy dandy diagram. But, okay, first things first, 1 plus 1 over 24. Ugly, horrendous, I hate it so much. We are going to be working with 25 over 24 instead. And the next thing that I notice is that this is a right triangle, and one of the Pythagorean triples is actually 7, 24, 25. And I'm pretty sure that that's going to be helpful later, even if I can't prove it yet. So what can we do? Well, we know that this side length is 1, and this side length is, 25 over 24. And we want to find this right here. So I think this is actually going to come in useful right now because 1 is 24 over 24. And so this leg, well, we could use the Pythagorean theorem to find it, but it'll be a little bit quicker and give us the same result to use the pre-established Pythagorean triple that's multiplied by a factor of 1 over 24. So then we'd get 7 over 24 as the side length. And then if we scroll back up here, we want to see the probability that the smaller of the two distances is no more than this. And we will notice that we could also have E over on this side. So what we're actually going to have is, let me make sure that I am solving the question and not its complement. What we're going to have is 2 times 7 over 24, or 7 over 12. And so if we check this, yay, that's the answer.
Cool. I actually would have, I think I may like your way better, but I can't decide yet. I might have cut the square in half down the middle and said that E can range from here to here and divided by 1/2. But I can't decide if that's worth the extra danger of forgetting to multiply by 2 at the very end. Maybe it is, maybe it's not. You'll never know. It's a secret I'll take with me to my coffin.
But you'll never know when you have a coffin, Evan.
It's so unfortunate. Unless I'm buried alive, but I don't really want that actually. Next question.
I could arrange for that, but sure, whatever you want.
No, I'm happy above ground. The whole numbers from 1 to 99 inclusive are divided into 3 separate lists. What is the smallest possible mean of the medians of these lists? Oh, I'm assuming, actually, I don't think it mattered, but we want the mean to be small. So we want, on average, the medians to be small. Yeah, and like William says, it's kind of intuition, but what I'm going to do is pardon that. I'm going to write the list 1 as one of my lists, and the list 2 as one of my lists, and then make the third list 3 through 99. And I think this is going to work because this way, these ones are basically the 2 smallest medians I can get. And for the third list, well, that median is also going to be as small as possible because I'm having numbers from 3 all the way to 99. And the middle is a lot smaller than if I did something like from 40 to 99. And then the middle would be somewhere here, which is kind of big compared to this one. And the median from 3 to 99, since they're consecutive integers, is 3 plus 99 over 2, or 102 over 2, which is 51. So the medians are 1, 2, and 51. And then I'll move over here and take their average, which is 1 plus 2 plus 51 over 3. I would combine them, but I don't want to. This is just 1, and 51 I like a lot more than 54. It's just me. It really makes no difference. So this is just 1 plus 17, or 18. For some reason, I seem to forget that 54 is 3 times 18 quite a bit, a lot more than I forget 51 is 3 times 17. Maybe because there are a lot of card deck problems where 51 needs to be divisible by 3. I don't know. Either way, we get 18. Oh, and Pamela and Kamal, they both agree with me. Yay. Let's check. 18. Hooray. Okay. That was nice.
It was very nice, yes. But you know what's going to be nicer, Evan? My problem. Maybe, we'll see. Let x be a positive real number less than 1. The infinite geometric sequence has a sum equal to that. Okay, yeah, no, my problem's definitely nicer. It looks ugly, but it's not that bad. We just have to remember our formula for an infinite geometric sequence. And that is going to be helped if I show you guys the problem I'm looking at. And then I can write down the formula being a over 1 minus r, where a is our first term and r is what each number is getting multiplied by. So here we can see that our first term is going to be x. So x over 1 minus something, and we then have to find that something. And as people pointed out in the chat, that something is simply negative x squared. And we know that this is equal to 1 over 2022. So now all that's left is to cross multiply, and we'll get that 2022x equals 1 plus x squared. And then we just do the quadratic formula. We bring this over, so we get x squared minus 2022x plus 1 equals 0, or x equals negative 2022 or 2022 plus or minus the square root of 2022 squared minus 4 times 1. And then we divide that all by 2 times 1. And then all we do is simplify. I don't like the fraction, so I'm going to get rid of it. 1011 plus or minus the square root of 1011 squared minus 1. And then, yes, we know that x has to be positive. No, we know that we know that x has to be positive and less than 1. And since the square root of 1011 squared minus 1 is less than 1011, we're going to take the negative. So that's 1011 minus the square root of, yeah, we don't have to take the square root, but we do have to find q. So, well, time to do some multiplication. 1011, 1011, 1011. That's multiplication the lazy man's way. 1, 2, 1, 2, 2, 0, 1. That looks correct enough. And then we, of course, subtract our 1, and that's going to give us our final answer of 1011 minus the square root of 10221220. Hopefully, I gonna be ugly either way. Wait. I don't trust that. X is P minus Q, find X. I don't think X is not going to be P minus Q. I'll bet you that's P plus Q that's showing up as my answer. And that definitely is what our P plus our Q is. So
that's good.
I think we did it right.
Yay. And I'm
Is
just
the
going to
problem
say,
nicer? It
is
bigger numbers, but it's also the problem that I solved and not the problem Evan solved, so that does make it nicer.
Yeah, and also I will agree. Infinite geometric series, from the heart here, you can tell they are awesome. They are great. And let's see, what is our next problem?
Well, Evan, it is 6 p.m. So I'm chill to keep doing problems, but we technically are not allowed to hold these lovely people hostage past 6 p.m. or 6 p.m. for us.
Right.
9, 8. It's been an hour, and that's all we're allowed to hold you hostage for. So you are free to go, but we will also stick around because we're having a lot of fun with you.
We are. Thank you for coming.
That depends on if Evan wants to do the next problem or not.
Yeah, we can do one more, I think. Let's see. Sure. Math is fun. You can never have too much of it. Unlike
That
some
is
other
true.
things. Well, you
Like
can.
physics, defenestration. You can have too much defenestration.
Yeah, physics maybe, I don't know, but math is good. Let's see. The base of a tetrahedron is an equilateral tetrahedron. The AMC 10s, they love tetrahedrons. Anyway, and it's an equilateral
This isn't
triangle.
an AMC 10, Evan.
I know.
And they give you a diagram.
Oh, they do? Oh, yes, that's so nice.
Yeah, that's why it says see next slide for diagram.
Okay. Base is edge length 6, all of the 3 edges, okay, have equal length. It's a regular tetrahedron. Given that all of the edge lengths and the height from the base are whole numbers, what is the square of the volume of the tetrahedron? Okay. The square of the volume. Oh, well, the first point about this problem, anyway, is that we're going to need the formula for the area of a pyramid, which is, I believe, 1/3, what is it? Base height? Yeah, 1/3 base height. That be, there, that's better. Okay, 1/3 base height. And we'll just fill in these numbers as we get along. Or I should say 1/3 the area of the base times the height, the corresponding height to the base. And I am going to quickly snip over this so I can draw better on it. Cool. So the area of the base, that's just, the base is a regular or equilateral triangle, side length 6, I think, right? Oh yeah, this is right, side length 6. And so it'll be side length squared √3/4, or 9√3, 36/4, or 36/4 is 9. And a fun way to remember it is that you have the side length s squared √3/4 for the area of an equilateral triangle. It's s, then 2, 3, 4, which is nice. But after a while, you won't need that. You'll just memorize it and have it memorized. Okay, we have the area of our base. That is 9√3. We can put that there. And now we want the height to that base. And this is the tricky part of the problem. So the way to do it is to sort of get this line, yes, down. And this will be at a right angle because this is the corresponding height from this tip vertex to the base. And then, well, we can find this new length that I'm going to draw, which is along the outer side of the pyramid. We can find that by the equilateral triangle. And that length, because if we just look at this rightmost triangle, rightmost face over here, 6, 6, and 6, it's a little bulging, but that length over there is going to be 3√3 because this is a 30, 60, 90 triangle. 3√3. Okay, and then we can't get this off a right triangle yet because we'd still need this little distance over here, the one that's in dotted red. And that's just us building a right triangle to get to this height, because Pythagorean theorem, it's always helpful. And this point, this base from this vertex, that's actually the centroid of the bottom triangle, or the point where all these green lines are equal. Oh, yeah. Did this say something about integers? I forgot that. All the edge lengths. Wait, the height from the base is a whole number. That's helpful. Great. And like someone said in the chat, yeah, William, the ratio of this bright green segment to this green segment is 1 to 2. And actually the dotted one is the same as the bright green. I should have drawn that more clearly, sorry. And then this is another equilateral triangle. So 6 and then 3 here for this length. And then the dark green plus the bright green is going to be 3 root 3. But then the bright green 1 to 2, bright green to dark green. So the bright green is 3 root 3 over 3. Sorry, wrong color. Equals root 3. The bright green is root 3. So root 3, 3 root 3. That's not right. The height is not going to be a whole number in that case. What did they say precisely? 6. Oh, oops. All the other 3 edges have equal length, but they're not necessarily 6. Darn it. Okay. But we'll still have our base. We just need to find the height. Let me clear this out. So sorry about that. Yeah, we'll make another right triangle, and this time remember that these 3 edges are not actually 6, but they are something else, x maybe. So by the same reasoning, we'd have this dotted line is x root 3. And then again from the base triangle, this here is 3 root 3. And now what do we, let's see. No, I'm just making silly mistakes to make this look hard. What is this?
Evan, if you're the inventor of math, how could you be doing it incorrectly? That doesn't make any sense.
Maybe I'm actually not the inventor of math after all.
You mean that person in chat lied to us? You lied to us?
People on the internet aren't always completely honest. I'm heartbroken.
Oh no! I think I might faint.
Whole numbers. Okay, let's see. We want the square of the volume. The height is a whole number. And this height here is by the Pythagorean theorem, root 3 by the square root of x squared minus 9. Because we can pull out the root 3, and then it's root 3 times what the hypotenuse, what the other base would be of a triangle with hypotenuse x and hypotenuse 3. And this is just something I sort of saw, but this under the square root will be an integer. If it'll be a positive integer, if and only if, I'm hesitant to say, x is plus or minus 5, but either way, x squared equals 25. And that's from the 3, 4, 5 right triangle. And yeah, I think it is only if, because on a side note, what this is telling us is that the difference between x squared and 3 squared is a perfect square. Or the difference between x squared and another perfect square is 9. And if you look at the graph of x squared, it goes like that. So the perfect squares, as they go up, and as you move further right, or as x increases, the perfect squares get farther and farther apart. So this is a more precise way of doing it, but this is not the time for that. Either way, we get x squared is 25. So what's in the square root is 4. And the height is then 4 times our root 3. We cannot forget that root 3. And that's gone because it's told us all we need to know. And then from here, it's just canceling. 1/3 9, 3 equals 3 root 3 times 4 root 3, which is 12 times root 3 squared, or 3, which is 36. And that's our answer. Just kidding, it's not our answer. They want the volume squared. Uh-oh, I'm getting nervous.
Don't be nervous.
This should not be a whole number here, or they would not. Oh, oops.
It's because of the base, Evan, remember?
Yes. Wait, no, the height, I believe, is only 4. Is that correct? Let me quickly think about it for a second. I am sorry. Yes.
Would you believe that solving a math problem for the first time, you might have to take a second and think?
Wow, I'm so sad.
Evan, a human, that I might not actually have suspected, but the rest of the stuff.
I am human.
Oh,
No, I'm kidding.
Evan, which of the squares have a bus in them? Select all.
Right. We forgot the root 3. The root 3 does not belong there.
The square root of 3, more like.
Yes. And then, wait a second. Something is suspicious here.
Oh, really now? I think it's you, but okay.
Oh, wait. Oops.
Evan, what did you do?
Okay, I see what I did. The other side lengths are integers. So we have x root 3. And so this height here, I'm not going to pull out the root 3 because the height doesn't actually have to be an integer. So root 3 times root x squared minus 9. And then again, 4. So I think we do keep the root 3 here because the height's not an integer. These are. And does 4 work? Yeah, it does. 4 root 3. I still feel kind of suspicious of this because I think I made a silly mistake somewhere. I really do. Because why would, if our volume was 12 by 3 or 36, why would they want that volume squared? Why didn't they just ask for the volume? What was the question again? Equilateral, all other 3 edges have equal lengths. Okay. All the edge lengths and the height from the base of the tetrahedron is a whole number. Goodness. Okay, so we're back to finding the height. I'm very sorry about this. The height, x squared minus 9 from what's other than the root 3, root 3 times the square root of x squared minus 9, which is the square root of 3x squared minus 9. Whew. Okay, now there might be a faster way, but I certainly don't know it. We can just plug in a few x and see when this, along with x, is going to be a whole number, which is an integer. And like before, we can again reference the graph, and we don't have to plug in that many, because after a while, perfect squares are going to get farther. Huh?
Evan, before you get too far ahead of yourself, you forgot to multiply the 9 by the 3 when you brought your root 3 inside.
Oh, thank you.
Oh, don't thank me, thank Chad.
Oh, I did not see that. Thank you, Chung Hao. 3x squared minus 27. Wow. Okay. Well, first one, x equals 2. Whoops. When x equals 2, 3x squared is 3 times 4, which is 12, which is less than 27. So we don't get a real number. I should not say x, not real. When x equals 3, the height is 0. I don't think that's going to happen. When x equals 4, 3 times 16 is 48. 48 minus 27, 21, not an integer. X equals 5. I'm thinking there must be a faster way to do this. Well, I don't see it. Okay, well, when x equals 5, 75 minus 27, 48. And that's not a perfect square. Huh. Oh, wait. Yeah, actually, I can save myself some time by saying x has to be divisible by 3, because then otherwise, what's in here is not going to be divisible by 9. So I'll clear this out. And then the next x we try is x equals 6. 3 times 36 is 108. 108 minus 27. Oh, yay, it's 81. Whew. So when x equals 6, we have, I'll move this so it's not writing over the chat. Yes, Ethan, yeah, x is 6, right? And Patrick, thank you. I'll take a few deep breaths. Okay, that's better. X equals 6. And then height equals 9. Whew. And so our height is 9, right? Yeah, I don't see anything wrong with that. I hope there's nothing wrong with that. Okay, and then our volume is 27 root 3. Oh, good, there's a root 3. No. How can that have a volume 27 root 3? That's too big. Did I make another silly mistake? Let's see. Okay, x, we got x is 6. So then this x root 3 over here is 3 root 3. Wait, is x 6 after all? Oh, huh. Let's see, I think I am doing something crazy. Okay, 3 root 3. Wait, but this is 3 root 3. Huh? Hey, Megan, do you see what I'm doing?
I see what you are doing. And
It's crazy.
yes. I'm glad you're the one doing this and not me. Let's just say of that.
No, because I get x equals 6 here, and then that gives me the height is above 0. Yeah, it does. Okay, good.
The height should be greater than 0, yes.
Yeah, good.
Oh, also, for people who were asking what the problem is, I will keep talking so that Evan cannot take away the problem from you while you all bask in its glory. It's a pretty nifty problem, ain't it? And in the meantime, I will use my special powers to stare Evan in the eyes while he tries to question math. How's that going for you, Evan?
I'm going to double check the problem. Base equilateral triangle. Yes. Other sides have equal length. The edge lengths and the height from the base are whole numbers. Okay. And what is the square of the volume of the tetrahedron? Okay. Yes, I haven't missed anything from the problem, so I'm making a silly mistake. And in a competition, I would just start over.
Oh, Evan, you know what you could maybe try as a different strategy? You could draw your right triangle from the center, but have its hypotenuse be the edge of a pyramid and not down the face. So then you have a hypotenuse of x, a height of height, and a base that's double the old base.
Good idea. Yeah, because actually, you helped me discover it. This x root 3, this was from assuming that all of the edges were equal. Dang it. Me being lazy and not completely starting over when I misinterpret the problem has instead cost me another 20 minutes. Okay. Yes, that was a very good idea Megan had. So we'll draw a new right triangle. And then
when in doubt, if whatever you're doing doesn't work, do something else.
I agree with Megan. This red length is So it's in the base equilateral triangle. This side is 6. And this is the midpoint. That's going to be 3. And then because this is a 30, 60, 90 triangle, this little edge over here is 3 over root 3, or square root of 3. And then this hypotenuse, which is this side here, is 2 root 3. Yes. Okay. Yeah, I don't know what question number this is, but I sure hope it's not in the first 5, because otherwise I'll feel sad.
It's the perfect time.
Okay, 2 root 3. And then we have our 3 edges here, 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 and here. They are x. And then this height is a more sensible x squared minus 12. Square root of x squared minus 12 is the dashed white line by the Pythagorean theorem. Oh, wait, no, never mind. Sorry, I thought 5, 12, 13. That doesn't actually apply here.
No.
3x is 3x. Oh, if x is 4, yeah, then it works. If x equals 4, I'm writing over the chat again. So x equals 4. X equals 4. And then this dashed white line, or the height is over here, is equal to square root of x squared minus 12, which is square root of 4, or 2. That's nicer. And then 1/3 area of the base height, area of the base, a squared root 2 over 3, 36, I mean, a squared root 3 over 4, I misspoke, sorry. 36 root 3 over 4, or 9 root 3. Base, there's nothing wrong there. Our 1/3, there's nothing wrong there. And our height, we just spent an awful long time for a very small mistake, which is easier to do than I would like. But I'm confident there are no mistakes here. Yeah, everything looks good. So then after this very brief recap, we can finally calculate the volume of the tetrahedron, which is 6 root 3. And that makes more sense. I don't know why, but it just makes more sense for such a small tetrahedron. 6 root 3. That's not their answer, is it? They wanted the volume squared. Volume squared equals 36 times 3. 6 squared, 36. Root 3 squared is 3. And that is 108. That's nice. Okay. And did we make any mistakes here? 1/3 is good. Base is good. Height. Well, we used x along here. 2 root 3 along here. And we found that x had to be 4. And because perfect squares get farther and farther apart, the only x that works will be 4. So our height of 2 is valid.
Evan, once you're done with this, I'll show the little proof of why it's why that's the only thing. Yeah.
Cool. So 1/3, 9 root 3, 2, and 108 should be the answer. Does chat agree? Do we have any people left?
Okay. So really quick, we want to show why x squared minus 12 equal to some integer n only has the solution x equals 4, n equals 2. So what we're going to do here actually is we square both sides. X squared minus 12 equals n squared. And then we get ourselves a difference of squares. X squared minus n squared equals 12. Or x minus n times n plus x equals 12. So note that n is simply n plus x minus n over 2, and x is n plus x minus n over 2. So we need the parity of our two factors of 12 to be the same. And the only way we can do that is 12 is equal to 6 times 2. And so then we just plug that in and we get x and n.
Yeah.
Yes. And technically we have one question left, but I think we have enough time to solve it. Answer looks like 1/4. Then we go and check. Yay, we did it.
That was a lot faster than this one. But thanks everyone for sticking through this problem.
Yeah, it's been a lot of fun.
Oh, Gareth, I think the other Evan did the thing where you add star. And
Evan
some
definitely
stuff.
changed his name in Zoom. Yeah.
Yeah, the other one, not me.
Shoot, I should change your name, Evan. Just change it legally to something else.
I hope not. It'd be very confusing.
But it would be
Almost
funny.
Tell that to the IRS.
No, why would I do that? I'll just make you tell it. Or better yet, I'll just get one of your friends to tell it. They probably have dealings with the IRS already somehow.
Yes, knowing our friends, I wouldn't be surprised.
There's one, you know, the small child who loves chemistry like a lot. I'm surprised he hasn't been contacted by like the FBI yet.
I mean, he recently left to get a degree in chemistry, so maybe he has been contacted and they just want him to work for them.
Oh, true. He scares me. He's like younger than you. And he's terrifying.
Yeah. Gareth, there's just a genius chemistry student who used to go to our school and is now getting a degree.
Yes. Yeah, no, this is just an actual school. This is just an actual story of what happened at our school.
Yeah.
It's not really a joke. It's just real life. How many people do we have? 27, and we might still be live on YouTube. So that's why I'm choosing to not say his name.
Exactly. Yeah, there are laws we do not want to break.
Yes, but